In this video, we are finally going to get to the mean value theorem. We have been working on this for a while. We started by introducing the extreme value theorem and the local extreme value theorem, and we used both of them to prove Rolle's theorem. Now we are ready to use Rolle's theorem to prove the mean value theorem. The mean value theorem is going to appear not very interesting at first, but we care about it not by itself, but because it will have a lot of cool applications. As a reminder, this is what Rolle's theorem says. I begin with a function that's defined on an interval a,b, closed and bounded, including the endpoints. If I assume three conditions, I assume that the function is continuous on the full interval, including the endpoints, is differentiable on the open interval, not including the endpoints, and the value of the function at the endpoints is the same, then necessarily there must be a point in the interior where the derivative is zero. For the mean value theorem, I want to get weaker hypotheses. I'm going to keep the first two. They're true for most common functions, so they won't cause trouble. But I want to remove the third hypothesis. And I want to know, if I only have 1 and 2, what kind of conclusion can I get? The conclusion will necessarily be different. And my first task is going to be to figure out, if I only have those two, what can I possibly conclude? But once I figure it out and I prove it, that is what we are going to be calling the mean value theorem. Let's begin with an example. I'm going to look at the function defined by this graph. This function certainly satisfies the first two hypotheses. It is continuous on the interval a,b, including the endpoints, and differentiable on the interior. But the values at the endpoints are different, so I cannot use Rolle's theorem directly on it. The trick is going to be to look at the line that goes to these 2 points, to the two extremes of the graph. I'm going to look at this red line, and I'm going to pretend that this red line is the ground. It is horizontal. Or in other words, I'm going to take this picture and I'm going to tilt it this way. And now, look, this line is horizontal. So looking at it from this perspective, now, in this graph, I can say that the value of the function at this endpoint and the value of the function at this endpoint are the same. So according to Rolle's theorem, I expect to have a point with zero derivative. And yes, I do. It's this point here. Now, zero derivative means that the tangent line at this point is horizontal. But horizontal means parallel to the ground, parallel to the red line. So what I concluded is that there is a point where the tangent line is parallel to the red line. Okay, with that conclusion, let me come back to looking at this picture normally and see what I can say. I've said that there is a point in the interior, and the point is here. This is the point C, where the slope of the tangent line is the same as the slope of the red line, so that the two lines are parallel. Well, let's find out what those slopes are. The slope of the tangent line at this point is simply the derivative at that point. And as for the slope of the red line, let me call it m for a moment. I can actually compute it exactly. The red line is the line that goes through these 2 points, and those 2 points are the points with x-coordinate a and b in the graph, so I also know the y-coordinate. So the slope of that line is simply f of b minus f of a over b minus a. So to summarize, I think I can conclude that there is a point in the interior where the derivative must be equal to this quantity. Well, I'm not sure what I'm going to do with that conclusion, but that seems to be the conclusion we can draw. And in fact, that's going to give us a statement of the mean value theorem. This is what the mean value theorem says. I begin with a function defined on an interval a,b, closed and bounded, including the endpoints. If I assume the function is continuous on the full interval and differentiable only on the interior, and nothing else, just with those two assumptions, then I can conclude that there must be a point in the interior where the derivative has exactly this expression I got in the previous page. And that's it. That concludes the statement. I haven't proven it yet. I will present a proof in the next video. But before that, a few comments. The mean value theorem doesn't simply say that this equation is true. The mean value theorem says that if these hypotheses are true, then there is a point in this domain that makes the equation true. So it's not merely an equation, it's all of this. If these hypotheses are true, then there exists a value in this domain that makes the equation true. As I had anticipated when I began this sequence of videos on the MVT, this theorem looks a little bit technical and not that exciting by itself. But remember, we don't care about this theorem for itself, but because it's going to allow us to prove a lot of nice consequences that will come later. Finally, I'll mention that like Rolle's theorem and like the intermediate value theorem, this theorem just tells me that there is at least one solution to this equation, but it certainly doesn't tell me how to find it. In the next video, I will present the proof.